let's start our program just on time. The first speaker is Professor Matthias Scheffler from MTI, Germany. Let's welcome.
Okay, thank you very much. Let me start actually in the beginning in telling you that although actually the workshop's just starting, I'm already very impressed. I'm seeing all the science which guided me here. I have seen actually the photo from the computer room. I think this seems to be organized in an extremely impressive way. And I wish you good luck and the students actually take advantage of these possibilities. So what I'm doing here is giving you some overview about a little bit the history and how this electronic structure theory evolved and the way how I'm looking at it. I'd like to start really with a very general way in looking at the history, how paradigms in material science and engineering have developed. Now, a paradigm means a way of thinking. And what you realize over the last, basically actually how mankind has developed is that the way of thinking is changing, and a new paradigm means a completely new line of thinking, a type of thinking which was not there before. Often people argue that a new paradigm means actually the old way of thinking is no longer valid. That's actually not true. I think at least in science, a new paradigm means we add a new line of thinking, which is very important. Now science, I would say, started something in the transition of the Stone Age to the Copper Age, which then became the Bronze Age, when people in using fire were able, in fact, to really do the early things, but nowadays is called metallurgy. So this was 6 million years before the way we really calculate time, BCE, and then basically it continued, and it's actually experimental physics is still, of course, a significant part of our life. Nowadays, maybe it's no longer standard fire. Nowadays, it could be a free electron laser where you can look on a time scale of less than attoseconds how electrons are moving in a molecule. But then at the end of around 1600, 1580, 1590, a completely new type of thinking started with people like Tycho Brahe, Johannes Kepler, Galileo Galilei, Newton and Leibniz. Namely, the idea that science can be described by analytic equations. Newton and Leibniz, in fact, were those who introduced to mathematics the concept of a differential. So things also were described in terms of a partial differential equation. And so that was a new way that you think everything which you can observe, you can also describe in terms of equation. And still, that is the way we are thinking about it. And here the symbol of this new paradigm, it started 1600, but the symbol which I'm using here is the time-dependent Schrödinger equation, which we all try to solve. Time went on, and around 1950, a lot of new ideas again came up into real life. The names which come to my mind are J.C. Slater, who developed Hartree-Fock theory in a way that you could really use it for material science, for solids. It was Metropolis et al., who introduced the Monte Carlo method. Actually, interesting paper, because if you look at the authors alone, I mean, it's really the Metropolis family, the Teller family, and the Rosenbluths. It seems to be a dinner type of thing, which they then wrote up afterwards, in introducing what is the Monte Carlo idea in describing science. Then there was by Bernie Alder and Wainwright, the introduction in the end of the 50s of molecular dynamics, which was more academic in the beginning, and Raman was the first to then introduce that to more realistic systems. And as you all know, in '64, the Hohenberg and Kohn theorem put what Slater had somewhat introduced by his feeling, I would say, into a solid, well-defined theory, namely density function theory. So this is the new paradigm that, in fact, it came, what was made possible by computations, which someone said you can solve equations numerically and you can really get results which you can use in a very similar way as we are using experimental data. In fact, you can use, for some cases, theory instead of experiments, and I show you some examples during my talk. Again, it took only a few years, and we are now, in fact, looking at a new paradigm, which was a little bit mentioned already, which is big data-driven science, which I will not really say very much now because I have another talk on this. So today in my talk, oh, actually, I have one thing here which I forgot to, which I wanted to remove, but now it's there. So basically, this new paradigm that big data are giving you a possibility to look into science, to see things which you would not see from studying small data sets. In big data, you see correlations which are really related to the big data, and that means you can describe science in terms of correlations. And there's a new thing coming with this, that you also give up a little bit of the idea that everything can be described by an equation. It could well be there's a lot of things, and I give you actually one example, in my feeling at least, where this is affecting all of us. There are things which you cannot describe in terms of equations, but you can describe them in terms of correlations by, for example, identifying patterns. The idea of that this is a new paradigm was introduced by Jim Gray on January 11, 2017 at a workshop of Microsoft Research. In fact, that was the last big thing he did, because 2 weeks later he went missing on a boat in the Pacific. But that was the first time I feel that the term the fourth paradigm and big data was mentioned. And as I said before, we will talk about this later, I think on Tuesday again. Today I'm talking about the theoretical sciences, about computational sciences, and as I just have said, on Tuesday it will be the NOMA, the novel materials discovery, or in general the idea of the fourth paradigm in material science. Here's another historic thing, which is a slide which is something like 20 years old, I think, which shows what we really want to do. It shows the problem of time scales and length scales, which we all, at the end of the day, want to tackle. So in principle, if you look what is important in real life, say, be it in computing, or be it in bridges and aircraft engines, you want something which works on a time scale of maybe micrometers, but maybe even meters. But you also want something which works on time scales which are pretty long. I mean, we are asking about something that, I mean, a steel should last for several, say 10, maybe 100 years or so. And so at the end we want a modeling, we want a description which is on the time scale of hours or years, on the length scale of meters. So this is what we really want. Whatever we do in our calculations and the things which you will learn during this meeting is aiming to get an understanding of things which are relevant on this time and length scales. This is what we want. But of course, there is a long way towards this, and that is what is called multi-scale modeling. And you will hear several things how to do this, but of course the main thing which we're discussing is the base of the whole thing. The base is electronic structure theory. That is, it tells you how electrons help to create a bonding between atoms, and that gives us a lot of ideas about stability. But then of course from electronic structure theory we make our way up by ab initio molecular dynamics, by master equation kinetic Monte Carlo, or actually Monte Carlo, and by other things. And you will hear talks. For example, I think Maria Troppens is talking about cluster expansion methods, and other talks telling you how really can you connect what we get on the electronic structure level, how you can connect this to things which are relevant at more realistic time and pressure scales and lengths and time scales. Now, the important thing, and that was actually noted 30 years ago, and that is still in fact a big problem, to be honest. So we have a multi-scale thing. We are going from one scale to the other one. One always has to take into account, and people are not really very honest very often on that, we need robust, error-controlled links with knowledge of uncertainty between the various simulation methodologies. we usually do one methodology, we then use this to really create the next one, and then we create the next one. But the links are usually not completely controlled, and you can very often not really going back to see what is really the origin. That is still an open thing we have to take into account when we do these calculations. Of course, as we said already, the important thing in material science, electronic structure theory, is density function theory. I will talk a little bit about density function theory. I took most of the slides out because Waitao is giving 2 more talks on that. But a little bit of density function theory, of course, still is in my talk, as I'm very often given this talk, in fact. So this is what we all know, right? This is the equation we want to solve, and we want to solve it with as little approximation as possible, so to have a reliable description. So it's the Schrödinger equation, which has the kinetic energy of the electrons, the kinetic energy of the ions, the electron-electron interaction, the electron-ion interaction, ion-ion interaction. This is the Hamiltonian times the many-body wave function equals the energy and the wave function. So this is the time-independent Schrödinger equation, where the wave function is a very complicated beast. It depends on n electronic coordinates, and n is a big number, right? We're talking about a solid, so that is 10 to the 23 number of electrons. And of course the number of atoms, m, is also a big number, it's the same, 10 to, of the order of 10 to the 23. So this is the Schrödinger equation, which is determined by the atomic positions, by the quantum number of the nuclei, from nucleus 1 to m, and by the number of electrons. So these numbers control everything. So in the context of what we call later a functional, you could say this very complicated wave function, or the energy, is a functional of these numbers. The relation is that you have to solve the Schrödinger equation to get to something meaningful. This defines in a very clear way, uniquely, the many-body Schrödinger equation. That we realized very early by Dirac, that this is an equation which describes everything essentially exactly. I'm not talking about relativistic effects at the moment, but we can also introduce them. So we know the operators, we know all the interactions, everything is there. So there's not really an open question. Actually, there is only one open question, namely, you have to solve this equation. So you have an equation which is correct, but you cannot really solve that. And the reason why you cannot solve that is the long-range Coulomb interaction between the electrons. They enter an operator where you have the kinetic energy. So these things together, the kinetic energy together with the Coulomb interaction, makes this thing so complicated that we cannot solve it without additional approximations. Now, what are the approximations which we are typically introducing? The first one, which is generally accepted, but I also like to give a little bit of a warning, because there are many cases, I believe, where this is not really valid. But the first thing which is typically accepted or used is the Born-Oppenheimer approximation. And that means the first line is really exact. So this many-body wave function, which depends on so many variables, you could write down in terms of a sum, basically an expansion in terms of a basis set of coefficients, where the coefficients depend on the atomic positions, and wave functions, which are a function of the electron coordinates, and where the atomic positions are only, say, a type of a parameter. So in the following sense, that these wave functions which enter here are solutions of an electronic Hamiltonian, which is just everything which we had before, but only the electronic pieces, the electronic kinetic energy, the electron-electron interaction, and the electron-ion interaction. If you solve this thing, you get wave functions, and of course you can write the general wave function as a sum over these with some coefficients, which you still have to solve in going into the many-body Schrödinger equation. So this is exact, but what then is typically applied for is that in evaluating these lambdas and going on, one neglects the so-called non-adiabatic coupling terms, everything which is somewhat a derivative of these phi with respect to the nuclear positions, and one only keeps the lambda zero term. So if you only keep the lambda zero term, it somewhat means in a simple way that you always assume the electrons are in their ground state. Wherever the atoms are at the moment, the electrons are always so fast that they are in the ground state. It means that the dynamics of the electrons in nuclei decouple. Now, very often, in fact, the word dynamics is missing here. When you see that in books, that is wrong. You don't decouple electrons in nuclei, you couple the dynamics of the electrons in nuclei. Now, there are limits which we know very well. Polaron-induced superconductivity, a dynamical Jahn-Teller effect. You know that in principle there is the ground state of a many-body, many-atom system is non-degenerate, and if it would be degenerate, it will, in fact, the system will distort. But in fact, it could distort in a very dynamic way, and this would be very fast. And there is a question that there are some examples of one indication that the Born-Oppenheimer approximation may not be valid. There are some phenomena in the diffusion of solids where people discuss the limits of the Born-Oppenheimer approximation. Temperature-dependent band gaps. There is very clear indication if you look at the scattering of molecules at surfaces, when we have spin polarized systems in particular, relaxation and transport of carriers, and more. So there are several things where we have to be careful. But in fact, in many of these cases, being careful is certainly always important, but in many cases you can still start from the Born-Oppenheimer approximation and continue in a perturbation type of treatment, but in some of these cases the perturbation theory may also not really work. Anyhow, these limits can be severe, and these could be very interesting things, and I'm pretty sure that we will find more in the future, but we're still accepting it, and that means in everything which I am discussing, and I think in everything which is discussed during this meeting, we start from this equation. We start from the electronic Hamiltonian, which has the kinetic energy of the electron-electron interaction and electron-ion interaction, and this thing we try to solve. This is still too complicated to be solved exactly. Actually, but before I actually say that, I should say what is then the quantity which are important. The quantity which is important is usually called the total energy, which has the energy which is the ground state energy of this Hamiltonian which you just have seen, plus an expectation value of this lambda function, but the lambda function is very much peaked, so it's just the Coulomb interaction of the nuclei. And the first one you will see we can calculate from DFT. The second one is just a classical summation, which you can calculate together with the first one very accurately. The third one is the expectation value of this lambda function with respect to the ionic kinetic energy. Now, why do I mention that? Because there you see already a little bit of a limit of the Born-Oppenheimer approximation, but you also see it's not really very severe. If you calculate the total energy as a function of lattice parameter of interatomic distances, we would do a molecule would be an interatomic distance. If you have a solid, it would be the lattice parameter. This always looks somewhat like this. It has a very steep behavior for small distances. That comes from Pauli repulsion, and then it's somewhat getting more smooth and slowly moving on the right side. That means this is really not a parabola, it's asymmetric. If you look a little bit more enhanced, it's an asymmetric thing. And of course you all know there are 0-point vibrations, so the atoms will not be exactly at the minimum, but they will vibrate according to the 0-point vibration. This is the expectation value of this thing. And that means if you would do a measurement, you would find the average of these vibrations, and as this is not a parabola, the average is a little bit bigger than the A0. So the quantity which you calculate in DFT is not what you would measure. What you would measure is something slightly bigger. It's not a big effect, it's less than, so the difference is less than 1%, but still actually it's measurable, and if you do, and it has actually some consequences, for example, for the band gap of a semiconductor and so on. So it's clearly visible, but you can in fact use a Born-Oppenheimer approximation, but you see that the limits already start being relevant here. So how do we calculate how are we then dealing with this many-body Hamiltonian? And Vitao will discuss that in more lengthy, and I think he has a more general, I would say Levy-based type of explanation, which I also like very much. I just want to give you here the historic one by Walter Cohen. But I give it to you really in a very schematic way. So in principle, the idea is we want to solve the electronic Schrödinger equation. And let's assume we would have a set of all wave functions, a set of non-degenerate ground state wave functions phi of arbitrary n-electron Hamiltonians. So the proof by Hohenberg and Kohn was originally for non-degenerate, but that in fact has been easily generalized by Levy later, and also by Lieb, I think. But that's so not important. So let's just for the proof say this is what it was published. These are non-degenerate wave functions. Every Hamiltonian has one ground state, and we know in fact from the Schrödinger equation that if you have the ground state, there's only one Hamiltonian. So between the Hamiltonian and the ground state, there is a one-to-one correspondence. Then of course, if you have a wave function, you can always calculate the density from the wave function. And this is the equation which we also all know. It's just the expectation value of these Dirac delta functions. A wave function gives you a density. Another wave function gives you another wave function. And what they asked in their paper is it possible that two different wave functions have the same density? And what they've shown, and the mathematical proof is called reductio ad absurdum, which I like very much. So this is Latin. It means you start with an assumption. You just start with the assumption that this could be possible, and then you do a little bit looking at consequences, and then you find something which is absurd, which is wrong. And of course, if you have done everything wrong, that means actually the initial assumption was wrong. And so by reductio ad absurdum, they could show this possibility cannot happen. And that means there's one wave function, there's one density, and that of course means you can also go back. If there's a one-to-one correspondence, there's also an inverse. And that brought them, with a little bit more thinking, to the fact that yes, you can calculate the energy as the expectation value of the wave function, but you can minimize that, but you can also optimize an energy function of the density. If you just look at ground state density, there's one ground state density which minimizes your energy and gives you not only what is the true density for your Hamiltonian or for the problem you're looking at. Now that is a big advantage in thinking because the expectation value of the Schrödinger equation, this is very schematic of course, if you plot this expectation value of the Schrödinger equation as a function of many body wave functions, right? I mean this is something which has 10 to 23 variables, so this is really a lot of wave functions here, has one minimum. And if you start with Hartree theory, you know you will never reach this minimum. If you do Hartree-Fock, you also actually know that you will never, except in one very few cases, reach the minimum. But doing the optimization in terms of a Schrödinger equation is nearly impossible. And that's why, in fact, the way this is done in Schrödinger theory is you restrict the number of tick marks, basically, which you consider on this axis severely by Hartree or Hartree-Fock theory or by other theory. Density function theory shows that the same energy but can be plotted as a function of the density. And that, of course, is something which is only depending on 3 variables. And that made it possible that you could look for the minimum and even do maybe a functional derivative of this thing which you have there. So that was the conceptually very important step forward, which introduced the development of many good approximations and treatments. This is actually just some handwriting of Walter Kohn when he explained the difference in what is the Bohr model of electrons and nuclei, what is the Schrödinger idea of a wave, and what is density function theory. But what I wanted just to say is the next step after Hohenberg and Kohn was the Kohn-Shem equation just 1 year later, and that made everything practical. So Hohenberg-Kohn is a nice theorem, but you don't really know how to use that, and Kohn and Shem then made it usable. Replace the original many-body problem by an independent electron problem. So in principle, you know you have electrons which are interacting, but you replace it by an independent electron problem that can be solved. So that was really the motivation from the very beginning. You want an equation which is solvable. And that means we write down the functional as a sum, where the first term is the kinetic energy, and that is an important thing, the kinetic energy functional of non-interacting particles. In principle, of course, we have interacting particles, and if you would start from the Schrödinger equation TE, you would have actually the interaction or the operator for interacting particles. Here you say, let's just assume, or let's just take the kinetic energy of non-interacting particles. Then you have the interaction of the electron charge density with the nuclei. You have a Hartree term, density-density interaction, and you have something which they called exchange correlation term. Now, the issue is, that this thing is not known, and a lot of very good approximations have been done. And this is the main challenge, to find a useful approximation for this thing. Now comes a statement that up to, say, some years ago, we all were thinking that you can, in fact, improve things better, and there is maybe a true answer to it. I believe, actually, meanwhile, there is no true answer. So that is actually, for me, one example where you know there is actually a relationship, but you don't have a good equation. Or actually, you don't have the exact equation. So what is shown is, in Hohenberg and Cohen, there is a one-to-one relationship. But actually what is not shown is that there is that the exact functional can be written down as a closed mathematical expression. We know there is a relationship, but we don't know there is an expression. And in fact, the way I'm looking at it is saying it is just an algorithm. It's just a description. And the algorithm is the following. If you give me the density, I can look at the density honestly, and I can tell you, in fact, what are the atomic positions, because you see from the density where atoms are sitting. When you know where the atoms are sitting, you know also what the charges are, because there is a Fermi contact term which you can evaluate. You can integrate the density, and then you have the electrons. So the density gives you really these terms which I said before, which determines the many-body Hamiltonian. This term, of course, determines the many-body Hamiltonian. The many-body Hamiltonian determines the energy and the density and the wave function. So the relationship is, in fact, in this way. It's not that I'm telling you that there is an equation going directly from n to e, but there is an algorithm which tells me there is a one-to-one, or there's a very clearly described procedure I should go. But there are good approximations. And so what we have developed and what we have seen in density function theory is fantastic approximations on this exchange correlation functional. Now I show you one picture here of Walter Cohn, who passed away a little bit more than 2 years ago. Here you see him rollerblading in Santa Barbara. Where he was living when he was 75 years old. And the nice thing and the importance of density function theory you see in this slide. You see the number of papers, in fact, how they increased in red. But what is also impressive, which was not there before, is that the number of patents, where the patents really mentioned density function theory, is also really increasing significantly. And that happened, I mean, it was already markedly there when the Nobel Prize was awarded to Walter Cohn. So basically, this was already clear it's important here, but of course the thing is increasing, it's further and further increasing. This theory and the concept of this theory had enormous impact. In fact, this was also actually what controlled my career. So I started with density function theory a little bit earlier. So I started here, and I had the luck really talking with people like Art Williams at IBM, Yorktown, and so on. So I think this is the good advice, in fact. If you know there is some theory actually with this type of success, if you start here, then you have actually a good career in front of you. But of course, you never know actually how the things are developing. So this is the basic theory, and when we started it, and we are still doing this, the idea in the Cohen-Shem theory was we don't know the exchange correlation functional exactly, but we can determine it approximately. There is one theory where we know the answer, and we knew this in fact since many years before DFT. That is a system which is called Gellium, or a system where the nuclei charges are not really point charges, but everything is smeared out to be constant. And then the electron density is also constant. For this system, actually the first equation is even correct. So in principle, you can always write down the exchange correlation functional as an integral over a functional which is the exchange correlation per particle, which is also a functional of density times the density. So this is exact. But then the idea was, why don't you do something which is a little bit like a Taylor type of expansion? You have something which depends on a constant dark charge density, and you have corrections which have the gradients. And for this EXC LDA, local density, you have an integral over EXC Gellium, which is now a function of n, because n is no longer n of r, but a constant. And if you use that for different densities, you can integrate it over n of r and getting really the general local density approximation. So for this term, the answer was known well before density function theory. Actually, it was known for small densities by Eugene Wigner from 1938, and you see this dashed line here. And it was known by a very sophisticated many-body theory by Gell-Mann and Brückner for high density here. The question was, in fact, what is in between? And so in between, basically, people in the beginning were just interpolating. But then in 1980, there were very sophisticated calculations by quantum Monte Carlo calculations by Alder and Schiaparelli. Alder I mentioned before because he was introducing the concept of Monte Carlo in the 50s. Here, in fact, they were using quantum Monte Carlo to do the evaluation, and the surprise was in how to connect these things that this is the answer. So in principle we didn't do so badly before, but so this is in fact the local density approximation which is used. And let me actually say one thing which is also interesting, which actually I showed this on the next slide, I don't say that here. Approximate functionals have been extremely useful. So you start very often with the local density approximation, but then you have corrections which are gradients. I say something in a moment. For certain bonding situations, van der Waals, hydrogen bonding, certain covalent systems, this is actually problematic. For highly correlated systems, it's certainly problematic. For excited states, in fact, the theory, the way it's done, is not really meant for excited states. So you should not be surprised that it doesn't work for excited states. And I think we will have several talks. I think Lucia is giving a talk on GW and time-dependent DFT, and I think Claudia is giving on BSE. So you will see actually a lot of things about excited states because the exciting code is somewhat made for that. What is the alternative? Building on DFT, but in fact doing, I would say, a different type of theory. Now, the different approximations are typically grouped in what is called Jacob's ladder. Now, I call this Purdue's dream. Now, this is actually my phrasing. And the reason why I call this Purdue's dream is that he invented this name Jacob's ladder. And Jacob's ladder comes really, is a religious term. It comes from the Old Testament or from whatever. I'm not really so religious, but I read this. So the idea was that Jacob had a dream. So in principle, not Purdue had a dream, but Jacob had a dream that there is a ladder from earth to heaven. And on this ladder, angels are going step up one by one. And so Purdue's dream is there is a ladder in density function theory where the ground is Hartree theory. The first thing is the local density, which you just have described. The second one was that you also include terms which depend on the gradient. The third one is called meta-GGAs. Things depend also on the kinetic energy density. You can also say on the second derivative of the density. And you see that the functional gets more and more complicated. Number 4 level means you also accept Cohen-Shem wave functions. This is what is called hybrids. Becker is one of the important names here who started really a lot of these ideas. B3 Lip, Purdue, Berg and Enserhof, BB0, Heitz, Gusseria and Enserhof. So there are several hybrids which are now usually considered to be actually very good. Our favorite, I would say, is the random phase approximation, which is based on the adiabatic connection fluctuation dissipation theorem. Nowadays you can do this, but you cannot do this for production. You can go up to the highest level just to make sure that your calculations are good, and you do this for 1 or 2 cases. In general, you would not do this, but you should always keep in mind that the functionals of level 1 and 2 suffer from severe self-interaction errors. Actually, I wanted to say something before. Let me see how to go back. Actually, I wanted to say something before, just actually also which is I think a piece of understanding, this is a dash here. So this thing is called local dash density approximation because this does not mean this thing is local. So in American language you are allowed, you don't have to, but you are allowed to put dashes if you think there could be a misconception. Now, if you would have no dash here, people would think this is a density approximation which is made local. That is wrong. So what actually is done, as you have seen it before, you start from the idea of a local density, and this is the approximation. That's why there is no dash here, right? The generalized gradient approximation is you do the gradient approximation and then you generalize this. And that's why, so the dashing sometimes really tells you all about the physics of the thing which is behind it. Anyhow, the problem is that functionals 1 and 2 suffer from severe self-interaction errors. Level 1, 2, 3, and 4 are lacking the long-range van der Waals tails. So there are some short-range correlations of van der Waals type, but there are long-range van der Waals are missing. And that means if you have, say, weakly bonded two-dimensional systems, or if you have organic systems, you're really in trouble if you just do this. But there are ways to correct this, to adding these things. The only thing where everything is there is really level 5, where now error estimates are becoming possible. We have, in fact, a type of test set which we are building. Actually, it's a Chinese colleague here from Fudan, Igor Zheng, is just putting a material science and engineering test set where we compare a lot of things to the exact exchange and correlations in the random phasor approximation to see how severe some approximations are. Let me get back a little bit to history. So what convinced me, so when I started, that was in 1980, I told you, and that was when I saw some examples which I felt are really intriguing. And what is impressive to some extent is that when we do nowadays theory and computations, we are doing very much the same thing as what Marvin Kuhn and his people did in the 80s. We're doing it maybe for more complicated systems, but the philosophy is still the same as they did it. And this is a paper, a FISREF letter from 1980, but somewhat corrected in this FISREF B from 1982 by Ying and Kuhn. So Marvin Kuhn, who is still active, in fact, at Berkeley. And what they did is they used total energy calculations for different structures. So they wanted to study silicon, and they wanted to see if there is a way that theory can predict what is the ground state structure of a certain crystal. Now, silicon was known very well, and so that's why they used it. In fact, the volume which they used here was really normalized. So this is the experimental volume. It's just a normalization thing. So 1 is the experimental minimum. And so they did it for many different structures, FCC, BCC, beta tin, and diamond, and hexagonal diamond. And you see, the lowest energy structure is the beta tin structure. So they could show that DFT is accurately enough. With this, that was before the Chapelier-Alder thing. It was basically that we simply connected things good enough to predict that the lowest energy is the diamond structure for silicon. But they could say even more, because there is a common tangent between this parabola type of thing and the next parabola. The common tangent is called the Gibbs construction. And the Gibbs construction gives you the derivative of the straight line, gives you the pressure under which silicon should do a phase transition. So they could also look that there is a pressure-dependent phase transition from diamond to beta tin. This is what they did so many years ago, and we are still looking at these type of questions, but for other systems nowadays. But this is what they proved. There was another example, and this is what actually what influenced me a little bit more, but they don't have a nice picture. Art Williams was a great person. Who had all these ideas, calculated electronic properties of metals from 78. I think this was the first, what we nowadays would probably call high throughput screening. They looked for all the metals in the periodic table up to actually the end of the 4D series, from hydrogen to the end of the 4D series. They looked at the band structure, they looked at the lattice constant, they looked at some elastic properties and the stabilities and whatever. It's a fantastic, very impressive way in 78. I mean, so long ago when no one of you guys were actually around, right? Yeah, you. So this is actually how it started, and we are still in this philosophy, and this is again actually from the Marvin Cohen work. And we also look at, we want to understand bonding, we want to understand how stable is a system. So this is for germanium, for gallium arsenide, for zinc selenide. You see in germanium you have a covalent bond, that means the electrons are in the middle. Gallium arsenide, it's a little bit more already ionic, but still actually very much covalent. The charge density is more to the arsenide, and zinc selenide is very much ionic. So these type of things started so many years ago. We now can do it on bigger things, but if you really just think about it, what a computer is nowadays, and think that every 2 years the compute power is doubling, right? I mean, how little compute power they had at that time, and still actually that was possible is just amazing. Now, it took some years that this was generalized, that people also realized you don't want to do this only as a function of temperature and pressure, but you also want to, and under clean conditions. But in fact, if you are dealing with real life, you also have an environment, you have a gas phase. And that is called ab initio atomistic thermodynamics. So coupling DFT to thermodynamics was then the next bigger step, I would say, considering that a surface is in contact with a gas phase. And I just have a specific example here, but you can use anything else, but I always feel having a specific example is easier than having a generic one. This is for how is oxygen interacting with palladium, which was a very open question many years ago in catalysis. And what you should really calculate is not just what we said so far, but you should calculate, or you should consider that the number of atoms which you are interested in is not really known. I mean, if you have something with a gas phase, you don't know actually how many of the gas phase atoms will go to the surface. Or maybe if there's a temperature, how many of atoms of the surface will go into the gas phase. So you have to leave this variable also open. And that means you should calculate the surface energy, normalization is 1 over area. You have the Gibbs free energy of the number of oxygen atoms and palladium atoms, but you need to have this particle independent, and so the number of particles which you have here, number of oxygen, number of palladium, you have subtract that assuming there is a reservoir, a gas phase for oxygen, number of oxygen atoms times the chemical potential of oxygen in the gas phase, or number of palladium atoms times the chemical potential of palladium atoms. So in this sense, you can also use these parameters, the number of atoms as a parameter to see what is in fact happening. Will this thing be a clean metal? Will it be an oxide? Will there be something new happening? You just allow that the system decides how many atoms it wants really to have. So that means the reservoir, typically in oxygen, you have a gas phase. That is just simple thermodynamics. The chemical potential of an oxygen atom is a function of temperature and pressure. It has the so-called standard value, which is temperature dependent and normal pressure. And then it has a pressure dependent, which is just the standard way in thermodynamics, the logarithmic of pressure divided by the standard pressure. So that can be easily calculated. For palladium, it's even simpler because if you just want to understand how things happen on a surface, you would say there's always a piece of bulk palladium, and so the chemical potential of palladium is just the Gibbs free energy of an atom in a bulk situation. And with this thing, even if you would not know, and in fact when these calculations were done, there was no idea what happens on the surface. It's not so long ago, actually it's 10 or 15 years ago, I think. So you just say you have a palladium and you allow a few oxygen atoms, but you also allow many oxygen atoms, and you calculate this Gibbs free energy, which you have seen before, as a function of this chemical potential. Because the chemical potential, as you've seen, can be changed by temperature and pressure. And you have one line for different structures. Every structure which you would put in has a certain line. So that is actually one thing you have to do. You have to really think all the possibilities which come to your mind, and you have to do a calculation for these, and only what is the lowest one is relevant. It's the same way as Marvin Cohen has done it for the silicon, right? All structures, and the lowest one is the relevant one. Nature is doing the same thing. Nature is also visiting all possibilities, but the relevant ones is visited more often. And what you see then is in the lowest one, at certain chemical potentials, you have what is called a square root 5 structure, and then at some point you have what is called the clean one, is actually the most stable one. Now this is more the mathematical thing, which is nice because everything are straight lines, but you can translate this into pressure and temperature, and if you would plot it in terms of temperature here and pressure there, you would see that for very high temperature, you have the clean metal, what you all would expect, right? For high temperature, all the oxygen should go away. But then there's a surprise which people did not before. Before the thing forms a bulk oxide, there is in fact really a significant area for a surface oxide. And in fact, this region of surface oxide is exactly the region which is the important region for catalysis. And so it really also showed you put something in a sample to do catalysis, but in fact the reason why this thing is a good catalyst that you create during catalysis the right structure, namely a surface oxide, which is the one which is shown here. Another thing you can do, and I have to be fast a little bit on this, is again something which was done independent of experiment many years before the experiment. You can calculate the surface energies. This was for gallium arsenide or indium arsenide. There was a time that and you're still actually very interested in quantum dots at surfaces. Indium arsenide quantum dots at surfaces, because these are very good things for lasers. In fact, there are now quantum dots television sets even, I think, with very good brilliance. But many years we really were thinking about what are the possibilities of these. They have a discrete line structure, but no one had an idea what is the shape of a quantum dot, and there was no measurement to do this. But theory could measure the surface energies, and so the prediction of theory was that these quantum dots should have this type of shape. They should have 111 facets, and they should have 110 facets, and they should have a flat roof. And some years later, probably 4 or 5 years later, after the theory, there was actually first experiments succeeded, motivated in fact by the theory, succeeded doing STM and looking at very small quantum dots by STM, and in fact confirming that the shape which was predicted is the way we have it here. So very often you can do things which the experiment cannot do so nicely, or in fact experiment still has to develop further. So with this thermodynamics, you can do a lot of things for say, doping and defects. You can look how many defects are in a sample at a certain temperature, what is the surface structure, considering realistic, really even aggressive environments. You could look at order or disorder phase transitions, and as I just have shown you, the equilibrium shape of crystals. The only limits are, as always, the limits of density function theory. Is the theory good enough on the KT scale? But in fact, not on an absolute scale. That's what also saves us very, very often. The important thing in many cases in material science, if you can phrase it correctly or nicely, is that you look at energy differences. And here, in quantum dots, for example, we look at energy differences of one structure or one surface compared to another surface. And of course, this is thermodynamic equilibrium. And the question is always, are we really in thermal equilibrium? Now, if you would be in thermal equilibrium, you would be dead, right? So everything which lives, everything which is interesting, I would say, is not in thermal equilibrium. And so a real life situation looks more like this. You have, this is actually gold, which is also an interesting catalyst for some cases. Gold in the nanoscale is in fact a catalyst. Gold in other scales is actually this, let me see. And so what you see, this is room temperature. So at room temperature, a gold cluster is not a stable thing. It really vibrates a lot, but actually it's not vibrates, it fluctuates. It's nearly like a liquid. It goes to one structure and then it's vibrating, and then it's jumping to another structure and it's vibrating. You see, every few picoseconds, which are quoted, you go to a different structure and then it vibrates around the structure. And so it's only important that one of these structures is relevant for the chemistry you are interested in. So looking at a stable situation is very often not the right thing to do. Things are dynamic and much more dynamic than what we very often really think. And we have to look at all the metastable states as well. That is a big field, in fact, analyzing metastable states, where some of the metastable states are only visited every few picoseconds, but that's good enough. But some metastable states maybe can be also stabilized for a longer period of time. Let me give you one example, which I think is one of the nicest examples I know, which is the ab initio melting curve of iron. It shows you that you have a tool with density functional theory, and if you're clever, you can use it for something which before this work I would not have dreamed of. Namely, you can use density function theory as a thermometer. You can define or you can determine the temperature at the middle of the Earth by density function theory. Now, how is that done? So this is what we know about our Earth, right? So we know, of course, a lot about the first couple of 100 meters. And everything else, what we know here, we know somewhat from earthquakes or some explosions. If you look how the explosion waves go through the Earth, and if a wave is say, submitted here, and when it arrives here or here or here, you can really say there is an inner core which is solid, there's an outer core which is liquid, and then there are other cases. The important thing was the question, what does it really mean, liquid? What is liquid under these conditions? And what is the temperature? Because if you want to describe that, you also need to know what is the temperature. You can determine the pressure very easily, because the pressure is basically just the material which you have above that. So the pressure is something which is accessible, I would say, with a very good model, but there's no way to really get the temperature. Temperature can be measured, of course, for maybe similar situations, but in fact only similar situations. These pressures which we have in the Earth core are too high. There is an Envin-Diamond cell that you can put pressure, but not as high there. The only pressure, and you have big error bars. In fact, if you do the Ironman cell, you have significant error bars. There are some pressure measurements. You can do maybe an explosion, and in the millisecond of the explosion, you try to measure the temperature. That destroys your sample, but that is not so bad. But you still actually can get some idea, but that is also not a very clear experiment. But you can calculate, in fact, the melting curve. So the curve which separates the solid from the liquid as a function of pressure. Now we know here at this point at 329 gigapascal, we know from this earthquake wave type of or bomb type of waves, we know that at this point we have a phase transition between inner core and outer core. And what these authors have done, Alfvén, Gillen and Price, if they calculated, and this is the dot dashed curve, they calculated the melting curve of iron. Now we know that the material is iron with a few percent of oxygen, sulfur, selenium, maybe a little bit of tellurium as well, and carbon. But all somewhat only of the order of 1%. So more recent work including this as well. So this is the melting curve of iron. And that tells you, if you now know that this is the melting curve, and you say what is the temperature then at 329 gigapascal? You go here, you find 6,670. So DFT tells you the temperature at this point is 6,670 Kelvin. Even with the approximations which we have in DFT, the error bar of DFT is much lower than the error bar which we have in the so far experimental situations. So this is, I think, how you should use these calculations. You should think about an open question, and then you should use a clever way to do this. One thing else which comes out of it, the question is, what does liquid really mean? And you can then look in these liquid situations, and you find that a liquid iron under these conditions has very similar properties as the liquid iron which you see in steel factories at the temperatures which you can create on Earth. That means there is actually diffusion, there is fluctuations, and you know that this is how the magnetic field is created. So getting an idea about viscosity was also very important. I think it was just a factor of 10 higher than what we have on the Earth. Now I'm seeing that I'm running out of time, and I really wanted to leave some time of discussion. I wanted in principle to give you another example, which is now a more recent example from just 2 years ago, on another strong electron vibrational coupling. But I don't think actually, I think we'll actually jump over that. Let me just say that only in words that, I mean, I talked about the Born-Oppenheimer approximation, but this is not really a Born-Oppenheimer issue. This is really the question is, what can you do with a phonon description? Now, phonons, or the thermal vibrations, are very important, but you have seen the gold examples, right? You have vibration, then the thing jumps to another one. In this jumping process, the phonon picture breaks down completely. But you will have a very good, I think, phonon description here, I think by Fabio Caruso, if I'm thinking correctly, giving us really a description of what phonon can do and what they're useful. But in some cases, in fact, the phonon description may be not good enough. Let me just go to my conclusion slide. Come on. Where is the conclusion slide? Okay. So what I wanted to tell you where you are and what you still have ahead of you. I think there was significant progress in condensed metaphysics, but you also have to really realize that the knowledge which we have is still very, very shallow. Why I'm saying that? If you look, what do we know about materials? Now, materials is really at the heart of our society. If you think about new products, right, a new smartphone, or if you know, actually also in the health industry about a new bone or new teeth, I mean, this is all actually, I mean, there's a lot of development in new materials. We know already about 300,000 materials, but actually when I say we know that about 300 materials exist, inorganic materials. There are much more organic ones. 300,000 organic are synthesized so far. But what we know, when I say they are synthesized, we know the geometry. We don't know the properties. What we really know, elastic constants, from these 300,000, we only know about 200 compounds. You will discuss a little bit about how to calculate elastic constants to improve the situation a little bit. But very little is known, and if you really want to develop a new materials, you need more knowledge. Dielectric constants, from all of this we only know 300 or 400. Heat conductivity, just 200. Superconductor, thousands. Topological insulators of the order of 42 or something. So very, very little is known from what is there, and that means there are many more possibilities for new products, for new type of living. For almost every properties we have, we are below 1% of the coverage of what is really known. So I told you a little bit about the equations, the second paradigm, and I showed you what you can do by computations, going to the middle of the earth or getting an understanding of what happens in catalysis to learn about things which you cannot really get directly from the experimental situation. If you look at this situation here, and the time scales, right? I mean, this whole thing started 6 million years before our common era. From 6 million to 1600 is quite a long time. 1600 to 1950 is already shorter. From 950 to 2010 is again very short. This is what is called a learning curve. So if a group of people is learning something, it's an exponential curves that you learn faster and faster. So when we have the fourth paradigm here, I think the fifth paradigm is nearly ahead of you. And I think this is where you should work on. And this is actually I'd like to stop with. And the future is already here. It is just unevenly distributed, and you have to find where it is and then work on it. And I give you the duty to think about what is the next paradigm, which is probably already visible somewhere. Thank you very much.